Welcome dear children to the class of science. We have just completed with very interesting topic from our textbook, that is electricity. And today we are going to begin with another very interesting topic, that is chapter number 13, magnetic effect of electric current. Children, science is really an interesting subject, and I always feel that it is fascinating for all the children because it keeps changing and it keeps them challenged all the time. The ideas in science expands your understanding, whether it was discovered in the past or present. So I must say that it's exciting subject and it is mentally stimulating, and I hope you'll get the same experience while learning this topic, chapter number 13, magnetic effect of electric current. But before we actually start this topic, I want all of you to have a look at some of the pictures which I'm going to show you, and you all will tell me the relationship between all the pictures which you are going to see in a while. So just have a look at this. You all have experienced this when somebody comes to your place and rings the bell, press the doorbell. What do you experience? You can hear the doorbell. Have you ever thought on which principle this doorbell is working? Have you ever thought about this? Along with this, these are some of the pictures which you have seen many a times. A maglev train, then a crane lifting the iron junk, then an MRI machine. This though you must be using it now also while watching the video, headphones, then hard disk drive, telephone which we use at home, and microphone. So these are some of the images which I have shown you. I just want all of you to think a while and tell me what is the similarity between all these pictures. I'm sure some of you might have got the answer. All these pictures which I have shown you, all these things works on magnetic effect of electric current, and that is what we are going to learn today. So children, in the previous chapter of electric current, we have learned that electric current is flow of electric charges. And when the electrons are in motion, when they move from negative terminal to positive terminal of the battery, the electric current is set up in an electrical circuit. So that is electric current. In electric current, we have learned the heating effect of electric current. When the electric current passes through the conductor for quite some amount of time, the conductor gets heated up, and that is heating effect of electric current. And one of the best examples of heating effect of electric current is an electric bulb. The filament in an electric bulb gets heated up and then it emits the light. You have learned one more thing, like the chemical effect of electric current. In chemistry, you have learned about the process of electrolysis. That is the decomposition of hydrogen and oxygen by passing an electric current through the water. And that is the chemical effect of electric current. In the similar manner, today we are going to learn about magnetic effect of electric current. So let's go deep into the lesson and understand about it. Have a look at the picture on the screen, dear children. Hans Christian Ørsted, the leading scientist of 19th century, who played a crucial role in understanding the relationship between electricity and magnetism. He gave lectures which were very popular among the people, and during such lecture in the month of April in the year 1820, Ørsted carried out an experiment that was never performed before. And through this experiment, he gave the world the new discovery of a strong relationship between electricity and magnetism. Ørsted was performing his own experiment related with electricity in his laboratory, and he observed that whenever the electric current passed through the circuit, the magnetic needle, which was lying just near to the electrical circuit, automatically gets deflected. And this was the time when he realized that there is a strong connection between electricity and magnetism. Let us understand this with the help of the small experiment. So we'll take a battery, and to the battery we will connect the connecting wire. A magnetic needle is placed just above this connecting wire like this, and when you connect both the terminals of the battery like this, you will observe that the magnetic needle gets deflected. Now when you perform certain experiments and you get the results, you want to try out this different ways to check whether your experiment is correct or not. So the experiment was performed by changing its polarity, the polarity of the battery. And to his surprise, he realized that when the polarity changes, the deflection is in the opposite direction. And this was the time when Oersted realized that electricity and magnetism have a strong connection. But before we understand what is this connection, we need to know the properties of the magnet first. So let's first understand everything about the magnet and then move on to the connection of magnetism with electricity. So children, you all are aware that when you move the magnet towards a magnetic needle, the magnetic needle gets deflected. Why is it so? Because the magnetic needle acts as a magnet itself. And so it gets deflected when you bring a bar magnet near to it. Now suppose if you keep this magnetic needle away from the magnet, then it will always rest in north-south direction. Are you aware of Earth's magnetic field? The Earth has its own magnetic field. The North Pole and the South Pole of the Earth resembles with north and south direction of the magnetic needle. Now let's understand this. Children, when you bring the magnet towards the iron nail also gets attracted towards the magnet. It's not necessary that for the iron nail to get attracted towards the magnet, there has to be contact between them. There is a force of attraction between the magnet and the magnetic material. So we can say that this magnetic force is a non-contact force. I'll just explain you this with other example. You take a magnet, move it towards the iron nail, take it above in the air, you will observe that even the iron nail also move up and down. Now here there is actually no actual contact between the iron nail and the magnet, but still the iron nail is moving up and down, and that clearly shows that magnetic force is a non-contact force. Alright, now I told you that the iron nail moves up and down. Why is it so? If I take a bar magnet, then the area around the bar magnet wherein the force of attraction exists, that area is called as magnetic field. So in that area, the iron nail moves up and down. This area is magnetic field. Now, is this magnetic field constant throughout? Is the strength of this magnetic field or the force of attraction of this magnetic field is same everywhere? I'll explain you this with your day-to-day life example. Children, you all have a router at home. When you want a signal in your mobile phone, you try to bring your mobile near to the router. So you bring it close to the router, you feel still you're not getting the signal. What do? You bring the mobile very close to the router and you get the signal. And exactly is the case in case of a magnet. So a magnetic field is the area around the bar magnet, and this magnetic field is very strong near the bar magnet, and as you move away from the bar magnet, the strength of the magnetic field becomes weak. Like when you move away from the router, your signals are weak. So if you take a magnetic material little away from the bar magnet, its force of attraction reduces. That is the reason when this iron nail is brought near the magnet, if it is close near the magnet in that magnetic field, it will get attracted towards the magnet and finally it will stuck to the magnet. Alright. But now the question is, how does this magnetic field look like? Are you able to see this magnetic field? The answer is no. Magnetic field we cannot see. We don't know how does it look like, whether it is in the form of a line or what. No, it's just an imaginary thing which we can just experience. But to understand how does it look like, let's perform a small experiment. We'll take a bar magnet, and on the bar magnet we will keep a sheet of the paper. And we will mark north and south pole in this manner and start sprinkling the iron filings on this bar magnet. Then you tap this paper gently. After tapping, you will observe that this iron filings, they arrange themselves in a specific pattern. And this is the pattern of magnetic field around a bar magnet. These lines are called as magnetic field lines. So I can say that the magnetic field around a bar magnet looks somehow like this. That you have to just imagine it. We cannot actually see it, but we have drawn it with the help of a small experiment. You will observe that at these two places, which is the North Pole and the South Pole, there the magnetic field lines are very close to each other. So we can say that the magnetic field is very strong near the poles. And if you see at the center, the magnetic field lines, they are very far away, they are spread, they are away from each other. So at the center, the magnetic field is weak. Now I want to just find out from where these magnetic lines are originating. Do they have any direction? Are they moving in any specific direction? For that, we will perform another very small experiment. We'll keep a bar magnet in this manner. We'll take a magnetic needle and place it near the North Pole. You will observe that the magnetic needle will deflect and the south direction of the magnetic needle gets attracted towards the North Pole of the magnet. We will mark the north direction from the magnetic needle. Then we will place the needle on the marked spot. Again, you will realize that the magnetic needle becomes stationary in this particular manner. We will again mark the north direction in this way. Again, we will keep the magnetic needle and keep marking only the north direction in this manner and complete our path this way. So every time we are marking the north direction of the magnetic needle. Now you remove the magnetic needle and all the points you have to join and you get, a line like this. Now you can place the needle at different places and you will observe that every time you are getting lines in this manner. This shows that the magnetic field lines, they start from North Pole and they end at the South Pole. So this is very important thing which you have to note, that magnetic field lines, they start from North Pole and they end at South Pole, and inside the magnet, the magnetic field line travels from South to North Pole. So this is a small experiment to understand in which direction the magnetic field lines move. So this is very important thing for all of you to remember. Alright, so this is actually how the magnetic field looks around a bar magnet. And from this magnetic field lines, we get to know that this magnetic field lines, they emerge at the North Pole and merge at the South Pole, and inside the magnet, they move from South to North Pole. Then the magnetic field lines are closer at the poles, and this magnetic field lines, they do not intersect each other. This is very important. Magnetic field lines do not intersect at each other. These are called as properties of magnetic field lines, and usually these are asked for 2 marks. So please keep a note of this. So I hope children you understood everything about the magnet and its properties. We will continue this chapter in the next period. Till then, I want all of you to have a look at what all we have studied once again and revise it. Bye and thank you.